Newton's second law can be used to solve problems in basically one of two ways usually. You you'll usually know either about the kinematics of the situation ahead of time, or you'll know enough about the forces ahead of time to determine the kinematics. So, show you an example of both with the same basic setups. The setup will be we have a hill, and we know the gradient or the angle that the hill rises above horizontal. We have an object on the hill. All right. We'll know that the object has some mass. Perhaps you actually don't, there's anything that could be unknown in this. But let's say the object has some mass. What we can do then is we could either say, okay, I'm going to tell you the object's acceleration along the hill, or I would have to tell you, if I didn't give you that, the coefficient of kinetic friction if it's sliding, or the coefficient of static friction if it's not sliding. Perhaps I'd have to give you both. So I'd have to give you one or the other here. And with that information, so I can either give you this acceleration along the hill or these coefficients of friction. And with that, I can solve this in one of either two ways. Let's assume first solution, I give you the acceleration along the hill. Well, in either case, I need to draw a free body diagram for my situation. So what I want to do uh, is identify all the forces. And I haven't covered this in any other videos, but to identify forces, it's really good to say, okay, what's the object I want to know things about? It'll be the box on the hill in this case. So I'll put a circle around the box on the hill. And if the circle intersects with any other objects, those objects may contribute a contact force. In this case, I'm only seeing the circle intersect with the hill. So that means I can only get contact forces from the hill. The hill is a surface. So my type of contact is only a surface. So I have a surface contact. And immediately I can recall my catalog of forces and say, okay, surface contact can lead to a normal force and a frictional force. And they will both be as big as needed within limits to keep the object from accelerating through the surface plane of the surface, so perpendicular to the surface, meaning keep the object on the surface, or to either prevent the object from sliding along the surface. That's the biggest for the static friction has a limit. And if I'm beyond the static friction limit, then the expectation is I will have kinetic friction, which I can simply calculate based on the size of the normal force. So to deal with this, I need to make a free body diagram, and it's very useful to keep both sets of coordinate axes in the same picture, meaning anytime I have an angle for a hill between, say, horizontal and the surface of the hill, it's useful, in my experience, to have both sets of axes represented. So that's horizontal, that's vertical, and then this would be the direction of the hill, and this would be the direction perpendicular to the hill. All right. And so I might call this, I'm going to go with X. So I'm going to say X direction is along the hill. Y direction is then perpendicular to the hill. And then I'm going to say vertical. I'm going to call that Y prime. And I'm going to say horizontal is X prime. Put my dot on the origin. That's the object. That's the box. So in this moment, we can now go to our catalog and forces and just say which forces should exist. Well, object has mass, therefore object should have weight. Weight points down. That would be along the y prime axis. So I'll have weight. All right. What other forces should probably exist? Well, The object is on a surface, and if weight was the only force, it would be expected to accelerate through that surface. Some component of weight would be perpendicular to the plane of the surface. So I'm expecting I will need a normal force. But normal force has to point perpendicular to a surface. So that would be along the y-axis up and to the left. Okay. Uh, I'm also expecting that if this is a real surface, that it may have a frictional force. So I could have some force of friction. It could point that way. Right. And so in dealing with this, it's easiest for me to work along the axis of the acceleration. So in this case, the acceleration will be noted along the hill. That means we would have AX equal to something, could be 0, but AY should be 0. That means that F net in this situation is going to be equal to F net X because the direction of the acceleration is in the X axis. And that F net Y would have to be 0. I have 0 acceleration in a certain direction. I must have no net force in that direction. And so these would be the guiding principles by which I figure out what, in this case, if I'm told the acceleration, I'd be figuring out how large the force of friction is. So this question would be, in this case, F equals what? And so the way to deal with this then involves knowing how to place this angle into that diagram. And the way you do that is you just transpose it to take up the position it already occupies, meaning it's between the hill, identify the hill in your free body diagram, that's the x-axis going up and to the right, and the horizontal, that's the x prime axis going right. And I can simply place my angle there. So the angle lives here. Once I get it placed in the exact same configuration of my free body diagram as I had it in my original diagram, then there's a simple game you can play to know everywhere where that angle should go. Basically, everywhere you see a possible angle, so the next one would be, for example, this dashed line, dashed curve there, that is not the equivalent angle. But when I go to the next angular kind of vertex, that will be the same angle. And that game just gets played all the way around. You can call it the angle, not game, angle, not the angle, angle, not the angle. So the next one would be not the angle. The next one would be the angle. The next one would be not the angle. The next one would be the angle. The next one would be not the angle. And you should get 4 reproductions of your angle anytime you have 2 axes like this. And so that's useful because now I can see where the angle I was given lives within my free body diagram such that I can use it to get components of any of the vectors that might not lie on the system of axes I want to use. I want to use the x and y axes. The normal force lies on the y-axis, so that's easy. I don't need to deal with components. Normal force will have a y component of something and an x component of nothing. Frictional force points along the x-axis. That's easy. Frictional force will have an x component of something and a y component of nothing. Weight doesn't lie on either axis, so I would have to find the components of weight. So weight in this case points down. There's my y-axis, and there's my angle. So I would have a y component of weight that might look like that, and an x component of weight that would look like that. So this is weight, that's wx, that's wy. And from this, I can solve for both. Wy in this case would be equal to w times the cosine of theta, since the y component is touching that angle. And wx in this case would be equal to w times the sine of theta. Remembering that w is just mg, so I can substitute mg's where the w's go. So how do I use this information? Well, Now I combine the second law and I say that F net equals MA, which means F net of a component must equal MA of that component. So what we can first start with is we can say F net Y is equal to 0. Right? That's because AY is equal to 0. Well, there are Y forces that have Y. There are forces that have Y components. So that means that the vector sum of those would have to be 0. In this case, I have a normal force that points positive along the y-axis, we might say. And I have the weight force that points negative along the y-axis, which I'll substitute immediately to be mg rather than w. And so all this is saying is that, sorry, I can't say mg, that's, gotta be careful. I should actually erase that. I'll keep it w for now. W, y, the y component of w, right? Which means I can rearrange this and say, okay, n, the magnitude of the normal force must therefore be equal to the y component of weight. Which another way of saying that would be normal force is equal to mg, that's still just weight, times the y component was w times cosine theta, right? All right, so now I know the size of the normal force in terms of the mass. So then what I could do is I could look to see what's going on in the x-axis. That's where my acceleration is. So I know that F net x is going to be equal to m a, and technically it's ax because a is ax in this case, meaning acceleration is along the x-axis. And second law says, okay, F net is equal to ma, but where does the F net come from? It comes from all the forces aligned on that axis. In this case, in the direction of the acceleration, which should be down the hill, I would have Wx. And subtracted from that would be whatever frictional force I might have. Right? Okay. So if the case was that I knew the acceleration and the mass, and I can extend this to make this mg times the sine of theta minus whatever frictional force. Well, in this case, I have all this stuff on the right. That's equal to this stuff on the left. This is just two different ways of defining F net. This is the cause side, and this is the effect side. All right, that's Newton's second law. And then whatever I'm given and whatever I don't have, I can solve for. So in this case, the frictional force would be equal to mg sine theta minus ma. And so based on the mass I have, I would therefore have whatever the friction needs to be. Now, you can get trickier with this because we also know, let's say the acceleration was something. If the acceleration was something, then we wouldn't have static friction. We would know we would have kinetic friction. And if you were given those values of mu k and mu s, well, we also know then that F, in that case, this would be an Fk, has to be equal to mu k times n. And we know from the y component how n relates to m. Meaning this could provide a direct path to figuring out what the coefficient of friction would be based on the size of the normal force if you knew the object was sliding. Um, what that means is even if I gave you less information, I could, for example, have you put that there. And then what you would notice is that every term would have m in it, meaning I could give you a problem like this where I didn't give you the mass of the object, because you would end up with something that looks like that is your friction if you knew it was kinetic friction in this situation. And what you would notice is mass is in every term, so mass no longer matters. And you would end up with something that looks like right? Um, and so in this particular case, I could actually have not given you the acceleration, but given you the coefficient of friction. So this is the second problem now, right? That's what we're saying. The first one, I give you the acceleration, but not the coefficients of friction. But if I told you it was accelerating, but didn't tell you how much, this same setup we just did, if I gave you the coefficients of friction, well, in that case, I wouldn't have had to given you the mass to solve for this acceleration. Right? That would just be, and provided you know theta and you know the coefficient of kinetic friction and you know the gravitational acceleration constant, you could solve for the acceleration. So that's just a quick little example of different ways that, second law can be used to figure things out to solve problems.